Hello and welcome to Cloud Design Principles. I'm Gary Bushy. In this video, we will be discussing cloud design principles, things to keep in mind when designing your application. Following these design principles will help make your application more scalable, resilient, and manageable. Keep in mind that this is an overview of the various principles and only touches on the basics and gives some, but not all, recommendations on how to achieve each principle. The first principle we will look at is self-healing. In the cloud, hardware can fail. Networks may have transient faults and, although rare, an entire service or an entire region may fail. By planning for these, your application can be self-healing. Your application should be able to detect these errors when they occur. The last thing you want your user to see is the unexpected error message showing up. Once an error has been detected, you want to be able to respond to it gracefully. If you cannot access a certain service, have a plan B, whether it's to store the task somewhere until the service comes back up, call the service in a different location, or something else. Then log and monitor the failures. Just logging the failure will not do any good if no one knows about it or does any sort of research as to why it has occurred or to determine if the failure has been resolved. How you respond to a failure depends on the application and the failure. A call to a SQL server that fails may be resolved by trying it again, but if an entire region goes down, then your application needs to respond in a very different manner. Most of the time should be spent planning for the smaller failures that are more likely to occur, like a network transient fault. The probability of an entire region going down is pretty small compared to a temporary network failure. A resilient application will route around any failures that occur. The last thing your application needs is a single point of failure. The question to ask is how much redundancy makes sense, taking into account that the more redundant a system is, the more it will cost to run. Each instance of a web app or a SQL database is going to cost money. An application that shows the number of vacation days an employee has is probably not as important as one that generates their paychecks, so probably does not need to be as redundant. If an employee cannot find out how many vacation days they have, it is not going to affect them as much as if they did not get paid. Some ways to increase redundancy include replicating your databases. Azure SQL will replicate your database within the same region, but you may want to use geo-replication to create another copy in a different region. You may also want to deploy a copy of your entire application to a different region. This not only makes sense in the case of a region going down, but you can also direct users to the application that is hosted closest to them, assuming your application is written to handle that. If you do deploy to multiple regions, use something like Azure Traffic Manager to automatically switch to a different region if your primary region goes down, but you should only manually switch back. This allows you to thoroughly check to make sure the region is running completely and make any sort of database verification checks that may be needed. One aspect of redundancy can cause issues. If you have multiple nodes trying to update the same database table, or two different tables that rely on each other, there can be contention, and coordination across the nodes is required. This coordination must be minimized so that the full benefits of scaling can be achieved. Some ways to help achieve this include eventual consistency, which means that you know the database will be updated, you just cannot guarantee it will happen immediately. CQRS can split the database into one for querying the information and one for updating the information. This can reduce the overall number of calls on each one. And by partitioning your data, you split your databases into shards so that different services can write to different shards, reducing the chance of contention. The main advantage that going to the cloud gives you is the ability to scale your application. By making your application scalable, you can add new instances as needed. Stickiness, or session affinity, occurs when the request from a client is always routed to the same server. This can limit the ability of your application to scale. Make sure any instance of your service can handle any of the requests coming in. By identifying bottlenecks, you can make sure that your application can scale. For instance, if your database is the bottleneck, adding more web servers will not help your application. A task that takes a lot of CPU or I/O should be offloaded or moved to a background task, if at all possible. This will minimize the load on your servers and can provide your users with a better experience. If they are waiting for a video to render, it would probably be better to tell them an email will be sent to them when it is complete, rather than having them wait for it online. Designing for scale in means that your application needs to be able to handle when your servers are taken away. If your application experienced a large enough load that new servers were added to handle that load, those new servers will go away once the overall load has diminished. your application needs to be able to continue to operate if a server it was using goes away. All Azure services have limits in the ability to scale. Some limits include the number of processing cores available, database size, query throughput, and others. If your application grows large enough, you may run into these limits and will need to partition around them. There are many ways to partition your application, including partitioning the database so that you can avoid a size or I/O constraint, partitioning a queue to avoid the limit on the number of requests it can handle, or partitioning your app service to avoid the maximum number of instances. Keep in mind that you can, and probably will, partition different parts of your application differently. While a database is a prime example of what to partition, consider partitioning your queues, other storage, and even the cache. While designing your partitions, plan the partition keys wisely to avoid having too much activity in any one partition at a given time. Partitioning by the name of a product probably would not work well, since there would most likely be a lot more products beginning with the letter B than the letter Q or the letter Z. Also, keep in mind that while individual services have limits, the Azure subscription has limits of its own. You may only be using 3 storage accounts, but other applications in the same Azure subscription are using 195 storage accounts. That only leaves 2 more that can be used, as each subscription can only have 200 storage accounts. Being able to monitor your application is crucial. The last thing you want is to find out your application is down when your customers start to call you and complain about it. Your application should be set up so all parts of it are monitorable. You want to be able to trace a path through your system to determine errors and bottlenecks, as well as log each state change. You want your monitoring to be close as real-time as possible so that failures can be detected quickly and avoided if at all possible. You also want to be able to use your traces and logs to find root causes of failures. By standardizing your logs and metrics, it makes it easier to get information across various services in your application. If each team used a different format for their log, it would be very hard to do this without some intermediate steps. Use a distributed tracing system that is designed for concurrency, asynchronous calls, and scaling. By including a correlation ID in the traces, you can follow the call across the many different services that get used. As this entire video series deals with PaaS, it should go without saying that you should use PaaS services rather than IaaS as much as possible. PaaS services are much easier to configure and administer, and there are no VMs that you need to patch and update. Always check to see if there's a PaaS service that you can use instead of hosting a service in IaaS. The list of PaaS products is quite large and growing every day. Some examples of PaaS products that can replace an instance of software running on IaaS include using Azure Web Apps instead of IIS, using Azure SQL instead of SQL Server, and using Azure Redis Cache instead of Redis. And there are many, many more. The video called Architectural Compute and Storage Decisions discussed some of the different data storage options available. By choosing the best one for your application, you can make it a much better application. Relational databases are great for ACID guarantees over relational data, but they are not the best solution for all types of data. Data in a relational database may require expensive joins to get all the data, and the schema is not very flexible. In large applications, it is quite unlikely that any single data store will be the best fit for all of your data. Feel free to use as many different data stores as needed. For instance, you can store a product catalog in CosmoDB to take into account the flexible schema. The images of the products could be stored in an object store, and the customer information and product sales could go into Azure SQL for the ACID guarantee. Also, take into account what your development team already knows or is willing to learn. It may be great to design a system using CosmoDB's MongoDB interface, but if no one knows how to use it, then there will be some ramp-up time. Your application will change over time, whether it's just a simple bug fix or major changes to the way it operates. By making your application able to change easily, you can plan for these changes. Using a pattern like microservices can help you plan your application to allow for changes. High cohesion means all parts of your service belong together. There is no reason to have a service that deals with computing taxes also generate the number of days off an employee has. Loosely coupled gives you the ability to change one service without affecting another one. If you need to update other services because of a change in one, then they are tightly coupled and should be looked at to see how to decouple them. Using asynchronous messaging allows the message producer to not care about the message consumer. If the consumer is down or changes how it operates, it will not affect the producer at all. By deploying your services independently of each other, you can update each one when it needs to quickly and safely. Bug fixes can be deployed when they are ready, not on a monthly or quarterly plan. This video discussed cloud design principles that should be looked at when designing your application for the cloud. By following these principles, your application can detect and avoid faults, scale out to meet your customers' needs, store your data for quick and easy access, provide insights into how your application is doing, and change as needed. The principles are self-healing to detect and overcome failures, redundancy to make sure there is no single point of failure, minimize coordination so you can avoid having two services contending for the same resource, design to scale out so your applications scale out and in as needed, partition around limits to avoid running into Azure limits, monitoring so you gain insight into how your application is running and find faults quickly, use managed services since it's better to use PaaS when possible, use the best data source to handle your different data needs, and design to change so that your application can easily be updated. Thank you for watching Cloud Design Principles, and I hope you will continue to watch the other videos in this series.